Okay, let's continue our study. Today, in this short video, we're going to, generalize what we just studied. Okay, we just spent a little over half an hour to lay the foundation on non-parametric estimation. We focused on empirical distribution, right? Let's go back to this graph. It's probably not good because if you apply the empirical distribution, it's discrete, right? And even you apply the smoothed version, it's somehow uniform for each region, right? Because it's a straight line. If your CDF is straight, that means the PDF, right? It's a constant. So each piece represents a constant CDF. So it's while you are trying to mix many uniform distributions. It's simple, but it may not be good. Right? That's why we are trying to come up with a more sophisticated concept to construct probability density function. Okay, we want a little advanced movement or development along this direction. This is what we call the kernel density estimation. Let's begin with fundamental ideas. Okay, that's the most important thing. Consider an observation. Previously, under the empirical distribution, what we do is we assign a probability mass 1 over n to this point, right? Each point has the same probability mass 1 over n. It's simple. But now, in most applications, our random variable x is actually continuous. In particular, if you talk about the loss distribution, right? So x is continuous, so you should get a density of it, right? A basic idea to generalize from a single point to a continuous interval is to get a symmetric interval around this point, right? So rather than assign 1 over n to exactly this point, we want to get an interval. We want to construct a symmetrical interval around this observation, okay? The length or the radius is b, which we call bandwidth. By the way, the length of this interval is 2b, right? But b, you can think it as the half, or has it the think it as the radius. Okay. What we do now is we no longer assign a single probability mass. We first of all we have an interval, and then we equally distribute over this entire interval. So it will be 1 over 2b. So we construct a uniform distribution. So this is what we meant. So instead of placing all the weight at a single point, we introduce a uniform distribution to equally distribute the weight 1 over n, right? So that's our idea, right? Okay, that means what we do is we assign this density 0.5 over b to this interval. Okay, of course, for any value outside of this interval, we put 0. So that's why it's exactly a uniform distribution. With that in mind, what would be the PDF? We already know how to assign PDF for each observation, but in total we have n observations. We have n observations, each with probability 1 over n. So naturally, what we do is fact by 1 over n, and then times by the not time, and then add all the densities together. Again, fi is defined previously down here, right? So each point may contribute to an interval, and intervals may coincide not exactly coincide, but may have overlapping areas, right? So let's say here is my f1, x1. So here is my interval. Okay, here's my x2. Okay, it has some overlapping areas. That is the reason why we need to sum up, because for any points, so let's say I have a point down here. I want to know the density for this point. It receives some shears from point x1. It also receives some shears from x2. Both points contribute to it, right? Of course, it's possible that more than two, right? It's possible that if you pick a relatively big bandwidth, there are three, there are even 4 points contribute to a single point. That's possible, right? Okay. But I think probably will not be more than uh, will not be more than I think will not be more than 3, I guess. Right? So 3 might be the maximum, but you probably need to check. But in most of our applications, it possibly will be 2 if there is any overlap. Okay, but again, we have this general definition. If you don't want anything else, but rather to compute. But the idea it's rather fundamental, and I want you to understand. Okay. Now that is technically speaking, we are done, but we want to do more, right? Because in this idea, it's fundamental, but what we have done is rather naive, right? We apply uniform, right? So one may immediately question why I apply a uniform distribution, right? What would be your natural guess? If I observe x1 or x2, I might want to play something like this. Here is x1, right? I want to play more weight. I want to put more weight around x1. And if a point gets further and further away from my observation, I would tend to put less weight instead of equal, right? And I cut, right? It may be nicer to apply, let's say, normal distribution, t distribution, or anything you want. Something goes long way, right? Although for this part, the impact is very, very small, but still has impact. Unlike uniform, uniform cuts off beyond here and here, right? Zero otherwise. Maybe you don't like it. Maybe even for this part, you also don't like it. You don't like the probability to be equally distributed, right? So in order to generalize, we need to do a little more work. So the thing we do is we don't want to write it as an interval exactly for x. Here, we don't want to write it for x. We want to write it to be, well, somehow unitized, right? We need to minus the observation divided by the bandwidth, and then it's between -1 and 1, okay? When we introduce a function. So let's define this function, right? So, well, you can see that they come from 11.17, right? They are very close, except the B part, right? Right. So other than that, they are identical. We call this kernel. Okay. The reason why I call it kernel is because, well, usually when we in the world of probability, when we say kernel, it's a density function. This is a density function, right? And it has nothing to do with the parameters, right? So you see here, I have a parameter of my observation, and then there's another parameter, which is the bandwidth. But in this kernel definition, it's just a uniform, right? It's uniform, -1 and 1, right? Which is the same for anything, right? It's invariant. But on the other hand, but in comparison, this is not invariant, right? It depends on your observation xi, and it also depends on your choice of bandwidth. Okay, with 11.18 is is better because everybody agrees what it is. Now what we do is we can easily define using this kernel, okay, kr, we can easily define the contribution function or contribution PDF, fi, okay? Just the note, phi I is nothing but x minus xi divided by b. And then we have this, okay? That is eventually our rewriting of f tilde, which we already defined. This is what we call the rectangle kernel function. Again, you know, that is because it's rectangle, right? -1 and 1, 0.5. Of course, this is a rectangle. So that's why we call it rectangle kernel function. But it does not need to be rectangle, right? Of course, you can call it the box. Box is the same as rectangle. You can also call it uniform because it's a uniform distribution, right? Then it gives us a way to generalize because under here, k is nothing but a uniform, -1 and 1, okay? We may want to try a different choice, right? All we need is density. So here's, first of all, it's density, so it should be greater than 0. And this is a graph. And the integral should be 1, right? So that's our original definition for PDF, right? There are two properties should be non-negative. The integral over the real numbers should be 1. So it's actually a PDF itself. So kernel is a PDF itself. Okay. Any function, any PDF can serve as a kernel. Okay. We have already seen uniform, right? In this graph, obviously this everybody knows, right? That's the Gaussian kernel, or this is just a normal, right? Normal distribution, right? But we always like to use Gaussian, of course, because Gauss discovered it. This is a Gaussian kernel. This box kernel is a uniform, or you can also call it the rectangle. You can also use this triangular kernel. Okay, the difference, as you can see from triangular kernel and rectangle kernel, is for a rectangle you put equal, well, not exactly equal, but the equal value of density. But for triangular, it has the same taste as Gaussian, right? It puts more weight for points that are closer to the observation, to 0, but put less weight when the points get further and further away from the observation, right? Again, it's right. So when the value is 0, is exactly at the observation, right? It takes the peak, and then when x gets further and further away from the observation, you decrease the weight. Well, you know, that's a nice idea, right? So that's why we have 3 shape down here. It's definitely not limited to this. You can come up with any density. Okay. The other two commonly used are triangular and the Gaussian. Okay. The choice is here. Right. It's rather trivial. By the way, this is standard normal. Okay. We already saw the graph, what it does, right? Now let's do competition. We have 10 observations. Looks different from the one we had before. But anyway, that's not the point. The point is how we can compute everything. We want to use rectangle. Well, of course, we can do more than that. Let's get to it. First of all, you need to figure out how many points contribute to your x. Right. So here we have bandwidth, it's 3. So the furthest that you can go is 11.5. Right. The shortest that you can go is 5.5. any points between those could contribute to 8.5. So let's say this point will not contribute because on the furthest that it can go is 8, right? It's not 8.5. So that's why given any x, you can do x plus b, x minus b to figure out what points might contribute to x. So we have 6, obviously, yes, right? And 7, 8, obviously, yes, and 10, obviously, yes. So I think my previous point was wrong because more than 3 points could contribute to any x, right? So it can more, then it means it can be a lot more, okay? Here we have 4, 6, 7, 8, 10, right? 12 does not reach because the lowest point that is reachable by 12 is 9, okay? Then we calculate, okay, what it is for the weight. By the way, it's uniform, so they all share the same. Right? So here b is 3, right? So for each fi is 0.5 divided by 3, so it's 1/6. And since there are 10 observations, so we have this already. And then all we need to do is to count. We just need to count how many we have. By the way, you should put this 0.5 with 3. Okay, then we count how many points. This is B. Okay, this part is always fixed. You just need to figure out how many points will contribute to your x. Okay, how many? 1, 2, 3, 4, 6. So for this case, it's 6. This value is 6. So that's why I can easily get the result. The next one is 11.5. So the interval would be 8.5 to 14.5, right? Then you count how many points you have. So let's see. 1, 2, 3. So you only have 3. So it will be half of the value you have. So it's very easy, right? So this part is always fixed. The only thing you need to do is to figure out how many observations fall under this interval. So this is the number of observations, okay, in this interval. Okay, so it's very easy to do. It does not show. I believe the textbook might give you a little bit more on the computation. So we can also do it for what? For triangular, if you want to do. Triangular kernel, okay? First of all, we need to identify the points. Those are the same, okay? And then the first value is 8.5. What do we have? Well, we can go back to the definition to review, right? So this is the kernel part. So we need it to be between 0 and 1 for the this means for the well, you can call it the standardized, right? It has the same taste as standardization, and then we know when we define this, it will be this kernel. So it's 1 over NB. Okay. So it's 1 over n. We have 10. B is 3. And then we need to figure out the kernel part. What are the points that will lay between? Remember here what we do is we want it to be greater than B divided by I. So in that sense, the points would be the same as what we discovered down here, right? So now let's do the analysis. 1 minus, what would be my first point? My first point is 6. 6 minus 8.5 divided by 3. Okay. Another way to think of this is 1 minus something less than 1. If you put the point is greater than 1, which means you don't need to include that. For instance, the first value is 5, okay? 5 minus 8.5 is negative 3.5. Divided by 3 is obviously then greater than 1, okay? You cannot have anything greater than 1 because you want density. It should be 1 minus something less than 1, okay? Since there are 2 observations with 6, so this has to be doubled. Okay, moving on to the next one. 1 minus, the next value is 7. If I'm not mistaken, yes, 7. I only have 1. Okay, keep adding. The next one would be, what is the next value? I have 2 8s. Times by 2, because I have 2 observations of 8. I have 1 11, not 11, 10, I believe. Yes, so I have 10 minus 8.5 divided by 3. Okay, then everything, let's put a square bracket. Okay, please compute. Okay, f 11.5 was the same, 1 over 10 times b, and then we need to figure out all the points. All the points for 11.5, we have 10, 12, and 13. 10 minus 11.5 divided by 3 plus 1 minus 11, 12. 11.5 divided by 3. And finally, we have 13 minus our x divided by 3. So this is how we apply a triangular kernel. Of course, we can also apply Gaussian kernel, but since Gaussian kernel, we don't know how to exactly get all the values. I mean, technically you can. It just it's more complicated. So basically, for Gaussian, you will need to use R, MATLAB, or any computing software to do the work. Okay. This is the graph for different bandwidths. So this is B equals 3, B equals 8. What do you observe? So when B gets bigger, this looks more and more smooth, right? If you can put it that way, because although neither of them is smooth enough, but when B gets somehow big, the contribution, it's you get more. So you can see the solid line, it's somehow more defined than the dotted line, right? Dotted line, it's somehow sharper, right? So it has more point than the solid line, right? Solid line, it looks slightly more smooth, right, than the dotted line. So that's what we can observe. This is with Gaussian kernel. Okay, you can see when B is 8, it looks almost smooth, right? It looks really smooth for the solid line now, but for bandwidth 3, well, of course it's smooth, but the shape is rather awkward, right? There are many humps, okay, that may not be really nice if you want to use it as a density function, but the solid line looks really nice, right? Although it's not exactly normal, but it's bell-shaped, right? It's nice. So let me end here for this section. We will continue in the next video for incomplete data. That's slightly more complicated.